We will now move on to a series of patents on very landmark inventions. First one that I thought I will tell you about is the invention of 3D printing. Charles Hull invented what is known as stereolithography. That is the way in which he kind of produced three-dimensional objects and which can be printed literally. Just like we have 2D printing on a piece of paper, you can also print objects in 3 dimensions. This is the famous patent he took in 1986. I'm not going to read out everything that is here in this, but what happened was, those of you who know how 3 dimensional objects are made, uh, you actually, or let's say plastic parts are made, what you do is that you have to make a mold, and once you make a mold, then of course you can replicate and get any number of these things, coming out from the mold. Now, but for those who know, it's very costly affair to make a mold, and if you are into R&D, you are not sure exactly what you are going to come up with, then you have to make many prototypes. Making these prototypes each time, making a new mold, can be horrendously costly. So it was with that thought that people started looking at that, is there any other way in which a 3 dimensional object, let's say from polymeric materials, can be made. The first such invention was made by this person in Berkeley, Swainson, and you can see method, medium, and apparatus for producing 3 dimensional figure product, 1977. I mean, way back, all right, and almost 9 years before Charles Hull. So, what is it that he was trying to do in this? And of course, subsequently, there have been several other patents that came out. Now, what they were doing was that they were passing two separate beams of light going through the through a liquid mass, and where those beams intersect, that is the point where polymerization takes place. You can think of it as light triggered polymerization. The two radiation would be of different wavelengths. Maybe with one I could do an initiation, and then it forms some kind of an intermediate, and that again is triggered or activated by another beam, and that's what finally results in the polymerization. So they had designed their systems in a very, very interesting way. Let me read out over here. In recent years, very sophisticated techniques have been developed for generating 3 dimensional objects within a fluid medium, which is selectively cured by beams of radiation brought to selective focus at prescribed intersection points within the 3 dimensional volume of the fluid medium. All of these systems rely upon the building up of synergistic energization at selected points deep within the fluid volume, to the exclusion of all other points in the fluid volume, using a variety of elaborate multi-beam techniques. In this regard, the various approaches described in the prior art include the use of a pair of electromagnetic radiation beams directed to intersect at specified coordinates, wherein the various beams may be of the same or differing wavelengths, or where beams are used sequentially to intersect the same points rather than simultaneously. So you can see different ways in which it is practiced. But in all cases, only the beam intersection points are stimulated to sufficient energy levels to accomplish the necessary curing process for forming a 3 dimensional object within the volume of the fluid medium. Then what he says is, what are the problems with this thing? And he says, unfortunately, however, such 3 dimensional forming systems face a number of problems with regard to resolution and exposure control. Because you see, even though we are saying intersecting at a point, but it's never like that, because they will also tend to converge and diverge, And so there will be points at which these beams are quite close and they can interact. And what can happen is that you can have a loss of resolution because of this. That it is not just at a point, but it will be along a cone that the reactivity will happen. And then he says there are other problems, the loss of radiation intensity. So these beams could also lose some energy as they're traveling from the outside of the medium inside, you know. And then he says the loss of radiation intensity and image forming resolution of the focus spots as the intersections move deeper into the fluid medium create rather obvious complex control situations. And then he talks about other problems: absorption of radiation, diffusion of reactive constituent, dispersion and diffraction. The light can diffract depending on the refractive index of the medium. All of these, what it did was that it made actually the job of working deep inside a medium quite complex. At that point, he started saying that I see problems in working deep inside a medium. Now, if this is what you have identified as your problem, what might be the kind of solution that you can consider? You don't have to give me a full solution. You can just give me an idea towards the solution.
If we can improve on the design of it, like the AutoCAD design or things like that, then we can actually have better quality in terms of printing.
Okay. Anything else? See, the approach that you must take to problem solving is that uh, he recognized, and I'm trying to put yourself in his shoes. That's what you must do. I'm not asking you to necessarily talk about your solution, but what he would have concluded. He found it difficult to work deep in a fluid. So what he said is there any way to work only at the surface? It sounds bizarre, but let us see how simple and elegant his solution was. What did he say? He said, and this is the definition of stereolithography, is a method and apparatus for making solid objects by successively printing thin layers of a curable material, e.g., a UV curable material, one on top of the other. That's it. That is what stereolithography is. What is it doing? Let's try and understand. And he gives two figures. Figure 1: generate solid individual laminae representing cross sections of objects to be formed. In other words, suppose let's say I have a hollow cylinder. Okay. What is the cross section of the hollow cylinder? What is the shape?
Circle.
A ring, right? And if the cylinder has a finite wall thickness, it will be a disc. Correct?
Yes, sir.
So what are we saying? That if now I keep adding rings one after the other, it will become a cylinder. There is no
Yes, sir.
better example of integration. When we learn integration and differentiation, this is integration. So what he's doing is each time he's forming a ring, and then it is going and joining with the ring below. And that's how he's successively forming all these lamina, and overall it will become a three-dimensional object. In other words, I grow a three-dimensional object out of two dimensions. Is that clear to everyone?
Yes, sir.
Everyone understood? Great.
Yes, sir.
Okay. So generate solid individual laminae and then combine successively formed adjacent laminae to form three-dimensional object. That's it. And figure 2, that is the concept. And then there are certain requirements in terms of the medium, the fluid medium that you are taking, and also the object that you are trying to create. Obviously, if I have to combine many such laminae, there must be some kind of an addition between them. So they must have some gluing characteristic. So what he says is contain a fluid medium capable of solidification in response to prescribed reactive stimulation. That's not different from what others have said, except that he's doing it on the surface. He doesn't have to work deep inside a liquid. Apply stimulation as graphic pattern at fluid surface. So we will see what it is. And then superimpose successive adjacent layers on each other. So let us try and understand a bit easier. Let's say I want to make this object. What am I doing? First, I will take the liquid and my I've got a pedestal, okay, which I will put right very close. I will use the beam of radiation such that it goes and polymerizes at one point here and one point here in the liquid. Moment it is polymerized, the polymer precipitates out of solution, means it's a solid. I move the pedestal down, okay, a little. Again, some more of this is allowed to polymerize, and gradually I build up the height. And every time this is being moved down from the top. Then I come to this part. So now my light is computer controlled in a way that now the polymerization that takes place is here and here. And this part goes and glues to it. And then after this is done, then I change the locations where the light is falling, and I basically have widened this thing out. And so now my polymerization will take place here and here, and it will go on and this will keep going down. And so finally, I have made my shape. Is that clear to everyone?
Yes, sir.
Okay, great. I want you to read this patent. It's one of the most beautiful patents, and he's also covered it in a very, very interesting way. He gives the requirements of this curable liquid, because this is what is being photo cured. And he says the curable liquid 22, that's this liquid, e.g., UV curable liquid must have several important properties. A, it must cure fast enough with the available UV light source to allow practical object formation time. Remember, all these things have to happen literally in sub-second time scales. Otherwise, it will take forever to make a 3D object. So it has got to be almost instantaneous. It must be adhesive so that successive layers will adhere to each other. Otherwise, if it doesn't adhere, the whole approach will never work. C, viscosity must be low enough. So what is happening? The moment this part has got polymerized and is going down, fresh liquid must come to the surface. And so that has to happen again almost instantaneously. Its viscosity must be low enough so that fresh liquid material will quickly flow across the surface when the elevator moves the object. D, it should absorb UV so that the film form will be reasonably thin. It has to absorb the UV radiation. If it is UV sensitive, that is. If it is not, then it won't work. It must be reasonably soluble in some solvent in the liquid state. That is, the resin that I take or the monomer that I take has to be soluble in some liquid. Either I use it as a neat liquid, okay, or I dissolve it in some solvent, but the monomer must be soluble. But the moment I polymerized it, my polymer must be insoluble. So it says it must be reasonably soluble in some solvent in the liquid state and reasonably insoluble in that same solvent in the solid state, so that the object can be washed free of the UV cured liquid and partially cured liquid after the object has been formed. So what they do is they don't do a complete curing. They develop green string so that there is addition and all that, and you can handle that stuff, and subsequently they do a post curing to completely cure it up. And sixth, it should be a non-toxic and non-irritating as possible. Ideally, the material should be that. This is how you define how exactly you will identify what are the requirements, and then different scientists can go and look at different aspects of a problem, and they can then overall solve the problem. Any questions from anyone? Did all of you understand it?
Yes, sir.
Yes, sir.
Okay. Let me put it the other way around. Is there anyone who has not understood anything? Very good. Okay. Let me ask you, can you think of any other way in which this invention can be practiced? And if there is any other configuration, particularly, that you can think of for this curing device, which can help to overcome some limitations, if there are limitations, anything that you see as a drawback, which you might be able to overcome? No? No one? Okay. Now you can see that although we are talking about intersecting at a point, it's quite possible that there would be some divergence of this beam, and they would be in close proximity, and there could be also some amount of polymerization that can occur in the underlayers. There the curing may not be complete, and it may actually give you some soluble resins which will just go into the solution, and those might never be again part of the product, which is this. So there could be loss of resin. It could also mean that there could be a loss of resolution, because of this kind of divergence of the beam, because everything is photoactive. This is one uniform bath. So Charles Hull came up with a very clever for subsequent innovation. And you remember that we said that it may be difficult to produce very large objects because the bath has got a finite depth. Okay, so it may be difficult to form large objects. So what Hull did was that instead of pulling down this device, can I pull it up? This is the other way around, okay, in trees. That's the kind of thing you need to keep in mind. So that's what he did. So now you can see that the device is in an inverted way. It's still stuck to a base. But now what you're doing is you are not pulling it down, you're pulling it up. What you have is a layer of the photoactive material here, and because you're pulling it up, you cannot really pass the light from the top, so the beam of radiation must now come from the bottom. See, the action must take place still at the surface over here. So the point is that the rest of the liquid must be completely transparent to this beam. Now, what it means is that I can have two dissimilar liquids. One is just a liquid which is the bulk of it, and on top of it there is a floating liquid of the photoactive material which will be cured. So this should be completely UV transparent, this stuff. And also, what else must be a property which it must have? One is that it must be transparent and it must not interact with the light beam. What else should it have? What property?
Partially soluble in the solvent.
Why partially? It should be completely
Not.
insoluble, because that resin part, I don't want it to dissolve in the solvent. I want it to be completely insoluble in this. The second is, of course, because it is at the bottom, so obviously it has got to have a higher density than the resin layer. Correct?
Yes, sir.
Yeah.
Yes.
So I hope you can understand that once you are thinking of a design, then you can automatically follow it up with possible properties which that system must have and the various components. The advantage of this is that firstly, I just need to put in a very thin layer of this reactive liquid on top. And so there is no wastage because all the rest of it is some other solvent, which is an immiscible solvent, which is just supporting this top layer. And I can have a very high absorption cross section on that thin layer. Effectively, that's where the curing is taking place. Now, the other thing is that you see, because my bulk of it is another liquid, what do I have to do? As it is polymerizing, I just need to inject fresh amount of liquid so that I always top it up. So I just make sure that I top it up to the original layer height because that's how I focus my beam. Okay. So I just need to do that. The other very nice thing is that because I do the bulk of it, as I told you, is some other liquid. So I can actually also put in not one resin, I can have also different resins. So let's say I do one a polymerization up to a point with one resin, and then I just introduce a separate resin over here, and so I can actually make composite polymers with this kind of a structure. The third is because I'm lifting up my stuff, you know, so I actually do not have the constraint of the depth of the bath in terms of the height of the object that I can make. So I can actually make an object which is much taller with this kind of a configuration. So you can see how very, very interesting things were done by him by just inverting the way in which you raise the object which is being formed. You know? So I'll just quickly read it out what he's saying. As will be apparent from figure 4 of the drawings, there is this figure 4. There is shown an alternate configuration for a stereolithograph wherein the UV curable liquid 22 or the like floats on a heavier UV transparent liquid 32, which is non-miscible and non-wetting with the curable liquid 22. By way of example, ethylene glycol or heavy water are suitable for the intermediate liquid layer. In the system of figure 4, the three-dimensional object 30 is pulled up from the liquid 22 rather than down and further into the liquid medium as shown in the system of figure 3, which was the earlier version. Now he says the UV light source 26 in figure 4 focuses the spot 27 at the interface between the liquid 22 and the non-miscible intermediate liquid layer 32. So that's where it is going to focus. You know, that is 27, this one. Okay, right here. And it says the UV radiation passing through a suitable UV transparent window 33 of quartz or the like supported at the bottom of the container 21. The curable liquid 22 is provided in a very thin layer over the non-miscible layer 32 and thereby has the advantage of limiting layer thickness directly rather than relying solely upon adsorption and the like to limit the depth of curing. Because earlier I had to maximize the absorption at the surface because otherwise it requires a higher path length for absorption. Then some of the curing will take place in the underlayers. Here I don't have that constraint because only the top layer is UV sensitive. Defined and some surfaces will be formed smoother and the system of figure 4 than with the figure 3. In addition, a smaller volume of UV curable liquid 22 is required because I need to just fill up and top up the surface. That's all. And the substitution of one curable material for another is easier. So if I want to make a composite polymer, I can first put in one resin. As it is polymerized, I lift it up, I put in the next resin, and it goes on like that. So that is much easier because I don't have to drain out the entire mass. Okay. Is that clear to everyone?
Yes, sir.
Yes, sir.
Okay. All right. Now let us look at a third innovation. And by the way, this patent has several other interesting things that it talks about. I'm not going to go through all of it, and I've sent you the patent, and I hope that you will read it. When I have got, let's say, a light focusing at a point, and you can imagine that you need a very sophisticated software to constantly move these things around, the light beam, depending on how it is required. Now, there are many objects where the object uh, is uh, is fairly simple in geometry. Okay, and so what I can do is that I can put a template on top of the resin. Okay, and so the template will be such, and I have a uniform collimated beam which is coming onto this template. Now, only where there is a hole, the light will pass through, and other places, of course, the light will get blocked. So, the object which I will produce will be aligned to the kind of template shape or the pattern which I have on the template. So, here I don't necessarily need to keep moving the light back and forth. I can just have one fixed light source and a fixed template. When you need to change, okay, the shape, then like for example from here to here, then obviously I need a different template. So that change of template is done, but those may be quite infrequent. It's not that you have to change the template all the time. And so he says over here, the system of figure 5. Now, one thing, of course, because I'm putting the template over here near the light source, in this particular configuration, the product which is being formed must necessarily be pulled down because the template is here. It may be possible to put a template also at the bottom, but putting a template at the bottom is not so easy. It's much easier to put it here because it's resting literally on the resin. So the system of figure 5 is similar to that of figure 3, but the movable UV light source 26 is eliminated and a collimated broad UV light source 35 and suitable apertured mask 36 is substituted for the program source 26 and focus spot 27. The apertured mask 36, that's over here. You have an apertured mask. You can see these are your apertured mask. 36 is substituted for the program source 26 and focus spot 27. The apertured mask 36 is placed as close as possible to the working surface 23 and collimated light from the UV source 35 passes through the mask 36 to expose the working surface 23, thereby creating successive adjacent laminae. That's what he's doing over here. As in the embodiments of figures 3 and 4, however, the use of a fixed mask 36 provides three-dimensional objects with a constant cross-sectional shape. Whenever that cross-sectional shape is to be changed, a new mask 36 for that particular cross-sectional shape must be substituted and properly aligned. Of course, the mask can be automatically changed by providing a web of masks, which are successively moved into alignment with the surface 23. This is your surface 23, right? So you can see that what is he doing? I mean, he is basically trying to protect his invention in as many ways as possible so that nobody else can infringe in his patent. And in that sense, a very comprehensive patent. It's also very interesting that he took this patent sometime, I think, around 1986 or so, right? It wasn't easy for other people to practice this because he had patented it, and so people had to wait till the patent had lapsed before they could get into the 3D business. That's why you 3D became popular after around 2010. I must tell you that there are many inventors and many companies. All they do is they keep looking at patents to find out when a patent is going to expire. So they are opportunists. They are not inventors, but they are good at finding this out. And I've seen many of these companies actually employ consultants, and all those consultants do is just find out which patent is going to expire, which year, and advise the company on how they should be ready to move in once the patent has lapsed. That's one kind of innovation, I suppose. And in fact, many times you find that the people who really do the invention are mostly way ahead of their time, and they have invented when there was no opportunity. They are forced to patent, they do, and by the time the opportunity really fructifies, you will find that it is all other people who are making the money, and the original inventor is, maybe he will get a, or she will get a name for being the inventor, but doesn't make the money. And I know that in many of our cases, I felt this sense of frustration when we did things, around maybe 2002, 3, 4, and I see things getting commercialized now, and our patents have largely expired or about to expire. And I was just wondering, what did we get out of it? Nothing. You know. So remember this. This is always a issue with patenting, and if you're too far ahead of your time, you may not be the one who makes the money. Of course, what clever people do is that they will do what is known as evergreening. Means I take a patent and then I make some further improvement and I take a subsequent patent. Okay. And so, like, all of these need not have been present, right in the beginning. Some of these things could have been introduced in subsequent patents. And that would have been like, or maybe a resin which performs even better, and which I don't reveal right at the beginning, but subsequently, I let a few years lapse and then I introduce it. In that way, maybe you can keep your patent evergreen, and so that you'll always be one step ahead of the other person. Even if your earlier patent has lapsed, you have gone on to do something a bit better. Let me, in fact, take you through one such example from our own work. It was done in England. I was actually deputed from ICI, Imperial Chemical Industries, to England to look after a part of their strategic research. Not the whole of it, but a part of the strategic research, especially in ICI specialty chemicals. So strategic research, I was wondering that what exactly my colleagues and I should be doing as part of strategic research. And one of the things that is good to go and talk to people. So I went and talked to the people, our potential customers and others. One of the products had become very popular in ICI, because ICI has thousands of products, was they had actually made a dental filling, which was a very non-toxic, safe material, and also it was visible light cured, not UV. This was the photo initiator. You can see that it is most active around 460 nanometer, and you can see this kid keeping the mouth open, and the dentist is basically applying light after applying the resin in the cavity. These were filling cavities and things like that. They told me, especially the marketing people, that we are going to have a big problem because this patent is going to expire in, I think it was about 2-3 years. I'm talking about around 1991 that I was there, 91 to 93. So they told me, by about 94 or so, this patent is going to expire. And they said, look, we really make a lot of money in this product, even though it's a niche product. Obviously, you don't sell that much of dental resin, but they said, but it's highly profitable, this business. And what they told me is that go and see how we might be able to maintain a competitive edge. That's all. Because the patent is going to lapse. I mean, there's nothing you can do about it. So that's what I've written here. The threat was that the patent was expiring. A way had to be found to evergreen the patent. Weaknesses now. Then that's all they told me. The question was, okay, they've told you something. So what do you do about it? What is the next step? That you should try and take. What would you do if someone left you with such a problem?
Check if we can make some minor modifications to patent and file another patent.
Correct.
So it
But
can be
the
extended.
minor modification must solve some problems, right?
Yes, sir.
I can't just make a minor modification for the heck of it, because then whether I have made the modification or not, nobody cares, right?
Yes, sir.
Agree or not?
Yeah, agreed.
Yes, sir.
Okay. So what then should be the first step? Well, the first step should be that go and find out if there is any problem with the product, which otherwise nobody might articulate because there's no competition, so everybody is happy. But if I'm faced with a competition, that I need to identify if there is any problem, which may offer me a room for improvement. It could be cost. For example, camphor quinone was a costly material. So if I can substitute it with a less costly photoinitiator, but it has to be non-toxic. It also has to operate in the visible region. So it's important that you identify that. At that time, I was very fortunate that I had some very brilliant people who were working with me. This person, he was a technician, John Yates, okay, and Ian Weddell had just finished his PhD at Oxford, and he joined my group. So I asked Ian, I gave him the problem and told him that, look, why don't you go and find out if there's any problem with this, which is like a unarticulated problem, which nobody has quite sensed, and see if that could be useful in trying and improving the product. One thing which I could make out was that obviously if you have to keep your mouth open for a long time, people get impatient, and kids will have a real problem keeping their mouth open for a long time. So obviously time of illumination is important, that I could sense. So that's why what we did was weaknesses of camphor quinone were identified, and what was found was very interesting. The speed of polymerization could be enhanced. At that time, and I'm talking about 91, and we, by the way, developed all these analytical techniques in our lab also. So as it polymerizes, anything that polymerizes acrylic resin, obviously I can monitor the how the double bond intensity is going down, and so from that you can estimate to what extent the polymerization has taken place. Ian actually monitored the polymerization as a function of time, but basically really estimating the amount of olefin that is remaining, okay, unreacted. And what he found was something very interesting. This polymerization has a long induction period. I'm just giving you for one composition. Don't think that this is really the ultimate. But for almost like a minute and a half, it does very little, and so you're keeping your mouth open and it's not doing much. So but then once it takes off, then what we found, it's a beautiful polymerization. It goes smoothly and goes to a very high level of completion, and you have developed enough of green strength. The rest of the polymerization can even take place while your mouth is closed in the dark. But but you could attain the desired polymerization up to whatever point is required for green strength with the camphor quinone. But it's, and with so many advantages, visible radiation, non-toxic, all that other stuff was there. But the drawback was that it required a long induction time. So I hope you can understand how to convert more or less an unarticulated challenge that is too broad, that see how we might get competitive advantage. So at that time, Ian, what he did was The place we were working in was the home of dyes, and there were various kinds of dyes that had been made because they were leaders in dyes. Later on, most of it went into BASF. But anyway, dyes was a big thing. So, there was a lot of samples which Ian had. I asked him that, can you just check what are the photoinitiator properties of those molecules? And because this is a quinone type of structure, camphor quinone, so I said, why don't you look at various anthraquinones? So he found many anthraquinones. In fact, he did some very clever stuff. Also, polymerizable anthraquinones, which can become a part of the resin so that it doesn't leach out. So, pretty smart thing Ian did. And what then he found was he was very excited. He came and he showed me this and he said, look, this one is polymerizing right away with no induction time. And he was very happy. But I said, Ian, you know how to monitor it over longer time periods because you have created the analytical technique to monitor polymerization in situ. So why don't you see over a period of time? Now, when he did this, what he found is it is really the difference between a tortoise and a rabbit. This was like slow and steady wins the race, this camphor quinone. This one, it ran fast, but then it kind of lost its speed, and the level of polymerization that we could achieve was substantially less, than in this case. So it had an early advantage, but a late disadvantage. So once you know such an observation, what might you think of doing? What can you possibly then pick up from these observations and try to solve the problem?
If I can look for a compromise, like
Right, very good. Can you put that a bit more explicitly? What do you mean by compromise? How will you look for a compromise?
it should have a lower induction time than the previous one, but
Correct.
at the same time, the conversion should not be as low as the fastest curve which was there.
Correct. So what you're saying is, so are you suggesting that we redesign and make a molecule like that?
Yes, it could be one possibility, or we could, if we can make some change to the existing molecule, which does not have a induction time. If we can make some change which makes it have some induction time, but it also
Okay.
increases the conversion.
Okay, good. One approach. Anything else? Any suggestions? Okay. Now, I must also tell you that sometimes you find these things a bit unfair. Like beyond giving the problem to Ian and he doing almost all of the work. I mean, I may have been in charge of the thing, but he's the one who did all the work. But ICI, we had about 8 patent attorneys, working over there. And so when ICI went through the what we had invented, they insisted that I must be the first inventor. So let me tell you why I was the first inventor, And I myself am telling you that I find this a bit unfair. I asked them, I requested them that can you please put him ahead of me because he's done all this work, and he's the one who went and identified the anthraquinones, etc. They said, look, for patenting, you need to have an inventive step. If you say that I screened a large number of anthraquinone molecules and found this, that would not be considered as inventive. That would be a routine process of doing R&D. They said we are not seeing inventiveness. Then I told him about how we were monitoring this polymerization. They said, yeah, okay, there is some novelty in that, but it's not inventive as such. So what happened was that when I saw these two observations, I asked Ian that what happens if I mix the two. That is, I can take advantage of a quick polymerization onset because of the presence of the anthraquinone. And the second was that maybe the camphoquinone part will kick in later on, and that I might be able to complete the polymerization. The other thing that you have to know is that to do toxicity studies is a very expensive and time consuming affair. So we knew that these are non-toxic molecules that we were working with because they had already been worked on before. So we didn't have any risk, and we did not want to take a risk of creating molecules, studying their toxicity, etc., because you don't know where we'll end up. We could do that, and we ended up with this stuff which you see as C. You can see that the completion of the polymerization was very fast. Now, actually, we don't wait over here. We just need to get green strength, which you can get maybe at some place even here or something. So you don't have to keep your mouth open all the way up to 600 seconds. We did that. Suppose, let's say I do it up to 40% polymerization. Suppose I build up enough of green strength. What you can see is that this would never be able to do it. Whereas here, I can do it over here. So we had a huge advantage, with this. The second was that this camphoquinone molecule was quite costly. So we said, let us also check whether I need to apply it in exactly the same equivalent amount, or do I have to do it in some other way. We looked at it, and what we found is that when we did these, we did not really find much of a variation in the usage level of the camphoquinone, and the anthraquinone was not an additional cost because it's a very cheap material. So we did not introduce any extra cost in achieving this. Subsequently, we had some compositions where we could reduce the camphoquinone usage. That was a very important thing because now we also made a cheaper formulation. This helped to evergreen the patent, and so the patent life, in a sense, could be extended by another 20-25 years simply because nobody would deviate from camphoquinone, and camphoquinone was still our baby, and this was non-toxic, so it would be very, very difficult for anyone to compete with ICI as far as this is concerned. Any questions from anyone? Did all of you understand it?
Yes, sir.
Okay. Now let me take you through another of these landmark patents. Velcro made kids forget how to tie a shoelace because you could just strap it on. That was the impact. I hope you understand impact. Could it impact millions and millions of people? You might say, what was so great about making kids forget how to tie a shoelace? But I'm just saying, in terms of impact, it obviously made an impact. But of course, the impact that Velcro made initially had nothing to do with our daily lives. It was the impact that was made to NASA. All these space suits, this, that, various things is where Velcro became extremely important. NASA were the preeminent consumers of Velcro at one time. What is the great thing about Velcro? Velcro is really a means of temporary addition. I can strap it on, and I can pull it out, and I can keep doing it over and over again. What are the other ways you might think of doing temporary addition?
Sellotape.
Sellotape.
It
Sellotape.
can be used for permanent, but it can be removed easily as well.
Sellotape, the rebonding is difficult. Beyond one or two uses, very difficult to stick it back. But you're close to that. Can you think of another product quite similar to sellotape which is used?
Some a magnet, like it can.
Very good, magnet.
Reopenable chain.
Reopenable
Zips, sir.
chain, yes, yes. In fact, it's very close to this invention, Velcro. We'll discuss. Anything else?
Ziploc.
Ziploc. Excellent. You see one thing, when you actually start having these questions and all, then you find that, yeah, there's so many things you can do. First, your mind becomes like a blank, and you struggle to think of anything. You know? But and usually when one person comes up with an idea, then other people come up with more ideas, and it goes on and on. Okay, good. You have given some examples. Can you think of any more? Now let's look at say you have your post-it pad, right? Those are nice peelable things, sticky notes. You just put it in and magnet. One of you mentioned Velcro, of course, is what we'll talk about. You can have sticky polymer blobs, which you use to kind of temporarily adhere things. Static electricity. You can actually you'll find that things come together because of static electricity, and then you can pull them apart. Suction pads. If you go to take an ECG, that guy actually puts the electrodes on your chest, using suction pads. If you look at these lizards and all climbing on the wall, even being upside down on the ceiling without falling off. And when people studied how do they actually stick to the surface, what they found is that they have suction pads, zippers, stapler, lids, and then you said openable chain. Now, what actually happened? This is a very nice example of basically inventing from an observation. This person, Georges de Mestral, and he was a Swiss engineer, and he was taking his dog for a walk. I mean, he used to go, and he found that many times, things these from the plants, some what are called birds, they stick to your trouser. The dog's fur is full of this stuff. So most of us don't care, right? You see this thing and then you just brush it off. But Mestral was interested and intrigued, and he said, why does it happen? Why does it stick? And then, he must have been able to think that if he can artificially make things stick, that maybe there could be very interesting applications, although it's not very clear what applications he had in mind at that time, because we're talking about the 40s, or maybe World War II or something. Maybe there were some requirements then, I don't know. This is no different from Newton seeing an apple fall, okay, and then thinking about gravity. Is it that that was the first time an apple fell? Not at all. It's falling all the time. I'm sure Newton must have seen it fall many, many times. But it is at some point you start thinking about it. Mestral was taking his dog for a walk, I'm sure, all the time. But one day he asked this question. Just because it is a routine thing you do every day doesn't mean I'll ask the question every day. And that is what is meant by like a eureka moment. And I asked this brilliant question. Why does it happen? Okay. And usually there's another thing that when you find eureka moments, and you'll find that actually once you have asked a question, you know, finding an answer is not always so difficult. And in our case, like street smart thinking, it's quite simple. It's the asking of the question which was the difficult part. Solving or answering that question was actually not that difficult. So what did he do? He put it under a microscope, again in the way Louis Pasteur put his tartrate crystals, under a microscope. And what he found is that there were loops and there were hooks. Okay, these birds had hooks, and many of these other things onto which they were clinging, they had loops. So hook was getting kind of closed in on the loop. So he says, the person who is writing this, on one particular hiking trip in 1941, Swiss engineer found burrs clinging to his pants and also to his dog's fur. On closer inspection, he found that the burr's hooks would cling to anything loop shaped. If he could only find artificially a way to recreate the loops, he might be onto something. No? And the result, Velcro. Okay, Velcro, by the way, means it's a composite word of velvet and crochet. Crochet is a type of stitching and knitting, and velvet. The well comes from velvet. You'll know that the surface of velvet is quite different from the rest of the material, and that's really the composite word, Velcro. And you can see the material had trouble gaining traction in the fashion industry. Initially, nobody was interested. They said, no, 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 we are comfortable with our buttons and things like that. But one of its most notable clients in the 60s was NASA. Okay, and it is NASA that really made Velcro famous. For most of these inventions, you need a client, and you need a visionary client. Uh, this patent, you can see the patent, of course, was granted much later, 1955. So it looks like between the discovery, his observations, and patenting, there was quite a bit of time. I'm not very sure why that happened, why he waited. But what is very interesting is we've seen this patent of Charles Hull, where he's so exhaustive, and it's a fairly long patent. Now, Mestral's patent is just 1.5 pages long, and he could say whatever he wants to say in 1.5 pages. That's it. So let me read out. It's so beautiful, beautifully written. Okay, and let us try and understand what he was trying to do. Now, broadly, it's all about textile engineering. Okay, textiles. And have all of you heard of warp and weft?
No, sir.
Okay, this is the classic way in which you weave a fabric. You have some threads which are placed longitudinally, and these are called warp, this stuff. And then what you do is that you take another thread, you can see how it is going in between. You take it like that, and so that's how you make a fabric which has got completely entangled, and so it can't come out. So these are the warp threads, and this is the weft thread. What happens is that when you are doing it in 2 dimensions, that's no problem, and most of our cloth, etc., are all in 2 dimensions. But what he did was that he wanted to make some kind of a raised structure which goes into 3 dimensions. The way it is done is that he had some rods, and the warp threads were being taken through that rod, so that it's in the form of a loop, and then we will see what he does with the loop. So he says, my invention has for its object a velvet fabric including a foundation structure constituted by a weft and a warp incorporating threads that are cut at a predetermined length so as to form a raised pile. My novel fabric distinguishes from the other similar fabrics by the fact that the raised pile is made of artificial material, while at least part of the threads in said pile is provided near its end with material engaging means, as required for adhering to a similar fabric or for scouring purpose. That material engaging means is the creation of hooks. My invention has for its further object a method for producing a fabric of the above type, according to which the raised pile is provided with its material engaging means by forming loops round the carrier and submitting the loops formed on the carrier to a thermic action with a view to giving them their final shape. It means that he was working with materials which could then be thermally set to make them stiff. After which the loops were cut on one side of the carrier so that each loop produces at least one pile thread having a hook-shaped end. Now, can anyone tell me what is the significance of paragraph 1 and paragraph 2? Well, if you look at it closely, the first paragraph is defining a product, and the second paragraph is describing the method by which that product is achieved. And the operating word in the second one is my invention has its further object a method, means this part is the process patent and this part is the product. So in that 1.5 pages, the guy is smart enough to have also covered both the product and the process patents. It's incredible. So bright. Whoever is the patent attorney who did this. And then fabrics of the type referred to are intended primarily for use as closing means or fasteners for garments, curtains, and the like as substitutes for the usual slider operated closing means or fasteners, or for buttons or the like attached means whenever a yielding invisible closing arrangement is of advantage. That's also another very important thing. It's not just a question of easy putting on and taking out. When you have shoes with shoelaces, the laces are always showing. But when I'm just putting it with the Velcro, there's nothing showing on top. So that also became quite a interesting fashion statement. You know. At one point, I mean, so people were doing it not just for convenience, because it became, and that's how fashion moves. You know, fashion is a funny thing, and it also comes a full circle. And today, people might find shoelaces better than that. You know, so it can also keep changing. I showed you already this. Now let us see how he is making this. Okay, so let us see what he's saying. When producing a fabric of the type illustrated in figure 1, this figure 1, I proceed in the same manner as for the production of special velvet made on bar looms. What is that velvet? Actually, as I told you, I mean, I have a rod which I keep above the fabric, and I take the warp thread and put it over the rod. This is my rod, and I've just put it like this. What do you think he does after that? You understood this special material. He's just putting it as a loop around this rod. So let's read. I proceed in the same manner as for production of the special velvet made on bar loops. As a matter of fact, it is possible to use for the formation of the pile a small transverse metal bars, round which the additional warp threads are caused to pass so as to form loop 6. Okay, so I've formed a loop, and this is my warp thread. So I have some additional warp threads which are basically going through that rod. Each small bar 5 is provided with a longitudinal groove 7. So this is my groove. There's a groove here, in which is guided a knife 8. This is my knife, adapted to cut the loop 6 open and to form thus the raised pile threads. So he's using this knife to cut it open, and so now it's cut. I form my hook, and this part is what is known as a wasted thread, because this thread I have no use for it, as such. If I just take a thread and cut it, will it remain like this?
No, sir.
It won't, because it's just a thread. It hasn't any memory of shape. So you may have cut it while it was still as a loop, but I'm not going to be able to retain this. So what he did was he took polymeric material in this loop. So it's not cotton thread, and which he could heat up and make it stiff. So it became thermosetting after heating up. When does he heat it up? After passing it through the metal bars and before cutting it with the knife. And he uses the metal bars as a means of passing electricity so that he can heat it up because of I squared R heating, Joule heating. Alternatively, he could pass steam and heat it up. So there are many different ways of heating it up. So he says, however, with a view to obtaining the hooks 4, I heat the bar 5 before the cutting of the loop 6, so that the thread extended over the bar may assume and retain the shape imparted to it by the bar. So I had my bar, I created my shape, now I stiffened it up with thermal action. Now I cut it. The heating of the bars may be obtained by making an electric current flow through them. Obviously, the carrier bars 5 for the loop may be heated as well through any other means than an electric current, e.g. the carrier bars may be hollow and heated by steam. So my bars need not be solid. It could be hollow and I pass steam through it and I heat it up. Or I could pass oil through it and heat it up. So what did he do? Look, in each line, he is giving all options by which the patent can be practiced, and therefore nobody can say, hey, you heated it up by electrical heating, I did it by thermal heating. He's covered all that. you know Maybe he's not covered microwave heating and things like that, who knows. Some of these things can also become relevant. After the loop 6 has been cut, the raised pile retains its shape, and each loop produces on one hand the raised pile thread 9. This is my 9 on the one hand, and on the other hand, ordinary raised pile thread 10, forming lost strands. So 10 is my lost strand. So that's how the hook is created. He did not make a hook and a loop. What he did was, he made two hooks. Let me ask you, if two hooks have to come together and get clung to each other, what should be the alignment of the two hooks?
They should be perpendicular to each other.
Absolutely brilliant. I'm so happy. So then, exactly as you said, obviously, if one hook has to go into the other, one has to be orthogonal to this, to each other. And it says, as apparent from inspection of figure 2, it is possible to superimpose two pieces of fabric of the type illustrated in figure 1 after having imparted to one of the two pieces a 90-degree angular displacement in respect to the other piece, and after turning them so that their pile surfaces face each other, the pile threads 9 of one piece engaging the pile threads 9 of the other piece through the cooperating hooks 4. Thus, as the number of hooks 4 per surface unit, say per square inch, may be high, the two pieces of fabric adhere together perfectly, and it is necessary to draw them away from each other with some energy. So, thermosetting and a hook, it doesn't mean that it is so inflexible that I can't distort the material. So, obviously, if I apply sufficient amount of force, then this thing is going to open that hook. That's how he was able to adhere these things. And also, I hope you can see that there are huge opportunities for uh, quantification, which I doubt anyone in the textiles and all who do all this stuff, I doubt if they know that. Suppose I ask that, hey, how many of these things do I need per square inch of fabric to be able to pull it out with a certain force? So I can vary the force with which I can pull it out, and so one will of course be the modulus of this particular hook, what kind of an energy I require to distort it, and the second would be the number. I hope you can see that if you want to do a quantification of the force that you would require to pull it out, you could actually go into very, very high end mathematics and physics. I'm sure that that's the kind of thing that NASA did when they were trying to, they didn't leave it to chance. They must have done a full calculation of applied forces, etc., and then tried to get the manufacturer to design accordingly. What kind of a force I need to apply to pull it apart? Is that clear? Did all of you understand Velcro? Did you find it interesting?
Yes, sir.
Yes, sir.
Okay, so let us now go to another of these great, great inventions, which is post-it pad. Quite similar. We're talking about temporary addition. Let us try and see how exactly this 3M company came up with post-it pad. By the way, 3M stands for Minnesota Mining and Minerals. 3M is an amazing company. 3M was, I don't know what is the thing now, but 3M was considered as the most innovative company in the world. And the other thing about 3M was, if you worked in 3M, okay, and I've heard this from people who have worked in 3M, they would ask you, you say something, and they say, will it affect 5 million people at least, your invention? And if they say no, they say, we are not interested. So they were really interested in products which have mass appeal. And look at the kinds of things that they have. Scotch Brite, which is used in the kitchen with that sponge and the abrasive surface. I mean, such a useful product to wash your buttons, to wipe your table, whatever. Wonderful product. Uh, so these are all the kinds of products that 3M is in. Why has 3M become very famous now of late?
Sir, I think it's for the masks, the COVID.
Wonderful. Very good. The N95 mask. That is a 3M product. Let me just quickly go through this before I go to post-it pad. Uh, and also so that you can see the trajectory of some of these inventions and how important it has become. Today, people talk about billions of pieces of mask. Forget about millions. India has a population of 1.3, 1.4 billion. World population is 6 to 8 billion. So, so you have to look at this. And by the way, a mask is not a new thing. Mask was first actually invented in China. It was to ward off the plague. And then there was this Spanish flu in 1918. And at that time, they had to really protect themselves against bacteria, etc. So, mask has had a history going into the first decade of the 20th century. Later on, because of pollution and particulate matter, especially if you're working in mines and it's so dusty. So, in fact, it's interesting. It is the Bureau of Mines. They were the ones who commissioned the work on the N95 mask. It was not for any virus. And the interesting thing was that when they were designing the mask, they got a part of their inspiration from products which had become very popular in the 50s and 60s, like the bow tie. You know, the bow tie, which is like a stiff bow. Okay. So they knew how to impart stiffness to fabric. We have seen also how Velcro was created because of imparting stiffness to fabric. But in this particular case, it was done by a thermosetting polymer. Okay. But there could be many other ways in which I can impart stiffness. The products, like for example, the bow tie and bra cups. So, bras with fixed shape had become very popular. Earlier, it was just a cloth and which people used to use as a bra. But now they could actually make these cups. And later on, people said, "Oh, I've got my nose, so if it can fit around my nose and my mouth, that's great." So they drew inspiration from the bra and actually made the shape of the N95 mask. Later on, what happened was that a, a Taiwanese scientist in the US, Peter Tsai, and working in a very unpretentious university, everything is not MIT and Harvard. He is the one who was the first to be able to demonstrate that he can make a mask with virus blocking property. The way he did it was that he made multi-layered masks, and he was able to show that by suitably making, we talked about temporary addition, electrostatic layers, static electricity. That's the kind of thing that you need. Viruses are also charged, and so they go and get attracted to these charged fabric, which is one of the inner layers of these masks, and so you can actually block off virus also. By the way, Sai actually retired, and last year, after this pandemic had unleashed itself, and there was a huge shortage at that time of these masks, and there were countries which were ordering 1 billion masks at a time. I remember France placing an order for 1 billion masks. And there was a tremendous shortage, and so Sai again came out of retirement and started looking at how to reuse. He's been doing a lot of work in this area. I will send you the paper of Peter Tsai. And I also, the point I'm trying to make is a lot of these so-called not the greatest sounding universities have done extraordinary work. And I find very useful work has come out of these places. So please don't ignore them. If you get an offer from some of these places, consider maybe there are brilliant people in some of these places. So keep that in mind. Coming back to the post-it pad, the idea of temporarily adhering things is not a new idea. It is not an idea that 3M came up with. That idea has existed for over 100 years. Soon after the birth of vehicles, motor cars, etc., people started making all kinds of fancy painting on the surfaces of vehicles because everybody was trying to show off their cars. So just like we saw how you can create a template for making all kinds of patterns and the 3D printing. So people would put all kinds of templates, and then they would, let's say, apply a spray paint. So wherever there are holes, so the paint would go and stick there. And then after that, you take out the your template. Then you can put in another template, and you can put some other paint. And that's how they would come up with all kinds of very interesting designs on cars. Graphic arts became a very big thing. And at that time, what people had done was because rubber is, elastic type of material, so they had used some rubber inspired products for temporary addition because the template had to adhere to your painted surface, because if it shifts, then you could ruin your whole thing. So it had to nicely adhere, and later on it had to be peeled off. And they found that with many of these kinds of things that existed, it was okay for once of use. I could paste it, I could paint it, and I take it out, and I then have to discard that template. It could not be reused. Probably in painting of car, etc., well, it was not a big deal that it can't be reused. But obviously, in many other applications, it would be important. All this information already existed, but the weakness was that you could stick, you could peel off, but you could not restick. Okay, and even if you could restick, it wasn't really so well stuck. So that was the weakness that 3M had been able to identify. And around that time, Silver Spencer, he was a polymer chemist in 3M. I suspect that 3M also had some very good engineers and physicists, and they must have thought of the concept of suction pads. How do suction pads actually operate? If you look at the paw uh, of a lizard and things like that, what you have is you have material and then you have got voids. When you go and pull it out and put it in, there's a vacuum kind of created from these suction pads. So what Silver Spencer thought was that suppose he can make a piece of paper where there is islands of resin. That is, the resin is not all over the place. In these particular things, the resin was all over the place. It was a pressure sensitive adhesive. But what he thought is that suppose he can make emulsion resins, okay? And if he can apply it in a way that those discrete emulsions will go and spread on the surface. There will be some resin, some void. So I have created a possibility of using it as a suction pad. And so that was the concept. This man, Silver Spencer, was able to make those microspheres through emulsion polymerization, and then he was able to apply those in a way that he got more of this ability to take it out as well as again put it back on. So those were the first posted pads from 3M. Then what happened was this guy was a very smart person. Again in 3M, Arthur Fry. What happened was that Arthur Fry got a sudden inspiration. Like we saw the bird kind of clinging onto the fur, etc. Arthur Fry used to go and sing in the choir, community choir. So he would be singing church hymns and things like that. And typically, what do you have? You have a book where maybe you have to sing 7 or 8 of these hymns, and you put these bookmarks, and and then one is finished, and then you move on to the next page where your next hymn is. And this is quite common, right? You do that for singing one song after the other. But what happens is, in many cases, the bookmark will fall off because I'm opening my book to read, and if you're not careful, the book mark can just fall off, and then you don't know which page. So when Arthur Fry saw the invention made by Silver Spencer, he said, "Oh, that's great! Now I can stick this paper on that page, and so it won't fall off." So that was his eureka moment, and he realized that this has got to be very, very important where people are leaving some instruction. You don't want a permanent instruction, and you say, "Can you please type out 4 pages of this?" Boss leaving a instruction for a secretary or this that, and that's how the whole thing proliferated as an idea. But let me also tell you that 3M, with all their innovation, etc., were sued by this man, Alan Amron, and he is the one who said, "Nothing doing. This was not your idea. I gave you this idea," and I'm sure Amron himself had no idea. He may have given the idea, but he had no idea that it will become such a big thing. But moment he found that array 3M is making a lot of money, and then he went and filed a suit against 3M. I believe Alan Amron was their consultant, and then he went and filed a suit, and he said it was my idea. And then they fortunately were able to resolve between themselves, 3M and Amron. And Amron further said that he withdrew his rights to any future claims against 3M. Now, what then Fry did was, we have learned, and when we were doing trace, and we saw another way. If I had to ask you if this is what I'm trying to make, can I think of another way of making it apart from making the microsphere emulsions which Alan Spencer had made? Can I do it by some other means? Anyone?
Repeat the question.
No, I'm just saying that Alan Spencer made emulsion. We know that an emulsion is basically spheres of lattices in a continuous medium, and then he was applying it in a dilute, sufficiently dilute form, so that all the emulsions did not get stuck to each other, and they formed discrete islands. Whereas, when I make a paint out of a emulsion, I make sure that all the particles glue together, and I get a surface coating. But in a post-it pad, it's like the same invention, except that I am putting these emulsions sufficiently far away so that they don't interact and they form islands. So wherever you don't have a resin, you have a void space. And so because of this unevenness in height, whenever I apply a force, I can create a vacuum-like environment. And so the question is that if I had to now do it by some other means, can you think of some other means of creating such patches of resin on a surface, which form islands or spheres?
Coagulation, if I can coagulate.
Coagulation
Yeah.
means you want to, actually, that's a good idea. You are saying if you can do it in situ.
Yes.
While applying it, if it can coagulate, I don't know. I mean, that's a good idea, but I don't know whether anyone has tried it, and whether you can control coagulation in that way. But yeah, certainly an idea worth looking at. I won't be able to tell you whether it'll work or not, but it's an idea, coagulation. Yeah. I was thinking that most of you being engineers will also look at some other engineering solutions. What Arthur Fry realized is that if, for example, I can spray this thing on a paper, because a spray which is coming out from a nozzle is coming out as what? It's coming out as a drop, right? So if I can spray it in a way that the drops do not coalesce, then I can again create islands, microspheres, by a completely different technology. Okay, and that's what he went and did. That he was able to spray this stuff on a paper, and the interesting thing is, my paper could be moving at very fast. It's a continuous process, like a printing press is moving very fast, and my spray gun is focused on one place, and as the paper is moving, it is getting sprayed. I might choose to direct the spray gun on only the edges. As the thing is coming out, I might apply it to one surface or both surfaces, whatever I want to do. So let us try and see from Arthur Fry's patent what exactly were the motivations and how he went about it. In the mid 1970s, applicants assignee introduced repositionable adhesive tapes and notepapers. So applicants assignee is 3M, and he was also an employee of 3M, and so was Spencer, which found an immediate acceptance and today provide a substantial volume of business. The adhesive utilized in these products typically present in a narrow band adjacent one edge of the sheet material, consists essentially of an adhesive binding layer containing numerous infusible, solvent dispersible, tacky, elastomeric microspheres. So it's not a continuous resin that typically have a diameter of 50 to 75 micrometers, as we saw over here. In another embodiment of this type of product, bulletin boards are surfaced with sheet material bearing the same repositionable adhesive so that notices, pictures, clippings, etc. can be temporarily adhered. I can either do it by Velcro type of systems or I can do it with this. Products of the type described in the preceding paragraph can be adhered to almost any substrate, including paper, even such weak paper as newsprint. Readily remove without delaminating the substrate and subsequently reposition. But let me tell you that the earlier post-it pads which I had used in the late 70s or early 80s were terrible. But today the post-it pads are unbelievably good. You can just paste it, take it out. It lasts for many, many such cycles. And then it says the force required to peel these products from a paper substrate is maintained in the approximate range of 8 to 80 grams per centimeter width. So how much force do I have to apply to pull out the paper? Okay, adhering paper. Right. So this is the unit. Products having significantly lower peel adhesion generally lack the ability to resist inadvertent removal, often falling off. So this is the minimum that you need to have. Products having significantly higher peel adhesion, on the other hand, tend to tear or delaminate weak papers at normal removal rates. So if you have too much of it, it will tear the paper. If you have too little, it may not stick properly and can fall off. So the peel adhesion is very, very crucial. Then is his wonderful invention. Numerous attempts have been made to achieve the results obtainable with microsphere adhesives by substituting more conventional pressure sensitive adhesives which typically have continuous coat. So pressure sensitive adhesives before were as I said, I mean they were continuous coats and rebonding was difficult, but the force that you needed to apply to pull it off was somewhere between 100 to 1000 gram per centimeter width. So what he did was he did not change the resin or the polymer. He took whatever is available and just changed the manner of application so that he can create microspheres. I hope you can understand what he did. So one approach has been to use a PSA, pressure sensitive adhesive, having inherently low tack, but it has been found difficult, if not impossible, to maintain consistent peel adhesion values. The nature of the note paper, backing and the thickness of the adhesive layer both profoundly affecting performance. Another approach has been to apply a thinner coating than normal, it being recognized that this will reduce peel adhesion. Unfortunately, however, it is almost impossible to prepare consistent coatings having removal values in the 10 to 50 gram per centimeter width range. Even when this can be done, adhesion will frequently increase upon extended contact to a degree sufficient to cause tearing or delamination. So it did not really fully solve the problem with the pressure sensitive adhesives. Then he says others have tried to obtain the desired degree of adhesion by locally deactivating portions of a fully coated coating of a PSA. That means this is something like that trace of overaction or underaction. So in this case you are doing overaction and then you are kind of removing parts of it. So he applies the coat and then starts finding some ways of taking it out. This technique but this technique has likewise proved difficult to control. the same problems are encountered in attempting to locally mask portions of a full coating of a PSA as taught in US so and so. So mask is a very popular thing, but making that kind of mask was very difficult. Then he says the prior art has also suggested applying pressure sensitive adhesive to only portions of a backing, leaving other portions free from adhesive. Thus, it has been proposed to make spaced adhesive stripes extending in either the machine direction or in the cross direction. So, only parts like as strips, you kind of coat. Also, not a bad idea. By and large, however, the spots were so large that attempted removal of the tape from newsprint will cause tearing or delamination. Prior to the present invention, then, it is believed that there has never existed a product having performance equivalent to that of the microsphere adhesives referred to above, but made with conventional pressure sensitive adhesives. And then what he describes over here is the way in which he has done it, and it's so beautiful. What he's doing is he's just carrying out a spray coating through his nozzles and creating these islands. And you can see that he's not taking necessarily an emulsion type of resin. He says over here, a method of making a removable and repositionable adhesive sheet product comprising spraying onto a sheet backing material, a solution. So I can take just a solution of a dissolved resin. That's it. Or dispersion. I can take a dispersion also, but I can take a solution. But I'm creating the islands by the way in which I'm applying the material on my surface. So that's what it does. And by varying the percentage of my paper that I have covered, something like 10 to 85%, he can end up making a fantastic sticky pads. And that's what is today the 3M post-it pad product. Any questions from anyone? Everybody
No,
has
sir.
understood?
Yes, sir.
Yes, sir.
Okay.